In this unit, we're looking at complex numbers, and you've seen complex numbers before, but let's refresh our memory. Let's start by talking about the imaginary unit I. It is the principal square root of -1. So if I have I raised to the power of n, this kind of gives us a way to figure out its value. If I'm taking I and raising it to the nth power, and n is a positive number, I can take that n, divide it by 4, and the remainder tells me what the value of I to the n will be. Similarly, if n is less than 0, same idea, it just kind of goes backwards from this. So there's two different ways that I would like you to take a look at this. So the first method deals with taking that exponent and finding the remainder when I divide by 4. So if I take 53 and divide it by 4, my remainder is 1. And if my remainder is 1, then I can think of it as I to the 1. So it's just I. Another way that I can look at this is to realize that the largest number that is smaller than 53 that is divisible by 4 is 52. So I could think of this as I to the 52 times I to the 1. Because remember that when I'm multiplying two things together that have the same base, I'm adding the exponents. So this expression is equivalent to this one. But I know that I to the 52nd power, because 52 is divisible by 4, I know that this is just 1. So it's 1 times I to the first power, which is just I. Once again, for this problem, I'd like to show the two different methods to do it. So we can take -18 and divide it by 4. And all we're interested in is the remainder. So the remainder would be 2. And so since the remainder is 2, I'd be taking I to the second power, which is -1. Another way that I can think of it as I to the -16th times I to the -2nd power. And this is just 1, so I don't need to worry about that. And I take I to the -2nd power, that's the same thing as 1 over I squared. I know that I squared is -1, and 1 over -1 is -1. So either way, you see that we end up with the same answer. So here we were talking purely about powers of I. Now we talk about complex numbers and how they can be expressed as A plus BI, and the A is the real part of that complex number, and BI is the imaginary part of the number. Now, if we think of a number that is A plus 0 times I, we know that that's a real number. So we could realize that all real numbers can be thought of as complex numbers. So imaginary numbers are all these numbers, A plus BI, where B does not equal 0. And then finally, if A does equal 0, meaning all I have is a B times I, then we call it a pure imaginary number. So we can perform some basic operations with complex numbers. And again, you've seen this before, and this concept is no different from a concept you learned back in Algebra 1 as far as combining like terms. So if I'm simplifying this expression, I would have 5 plus -2, and that would be 3. I combine the -3i plus the positive 4i, and I have plus I. And that's it. Take a moment and work through the Your Turn Below, part B of example 2. when we multiply complex numbers, I'd like you to think of this as the same process as when you multiply two binomials. So 2 times 7 is 14. 2 times negative 4i is negative 8i. Negative 3i times 7 is minus 21i. Negative 3i times negative 4i is plus 12i squared. And now comes the difference between multiplying two binomials and multiplying complex numbers, which is what we're doing here. What you need to realize here is the value of I squared. The value of I squared is negative 1. So 14 minus, let's combine our like terms while we're at it, 29i plus 12 times negative 1. Well, that's negative 12. And 14 plus negative 12 is 2, and then minus the 29i. Same idea here. 4 times 4 is 16. 4 times negative 5i is negative 20i. 5i times 4 is positive 20i. And 5i times negative 5i is negative 25i squared. So a great thing happens here. These cancel out. And when I take into consideration the value of I squared being negative 1, I have 16 minus 25 times negative 1. So this becomes plus 25. And I end up with 41, which is just a real number, not imaginary at all. And so what I want you to notice is the relationship between these two complex numbers. Notice that they are conjugates. So the conjugate of a complex number, if I have a plus bi, its conjugate is a minus bi. And so when I multiplied these two conjugates together, look at what happened. I ended up with a nice, neat, non-complex number. And so that's why we use conjugates to rationalize a complex expression where we have a denominator with a complex number. So let's rewrite this as 5 minus 3i over 1 minus 2i. And we're going to multiply the numerator and denominator by the conjugate of this denominator, which is 1 plus 2i. So in my numerator, I have 5 plus 10i minus 3i minus 6i squared over 1 minus 2i plus 2i minus 4i squared. These cancel out. Let's simplify. I've got 5 plus 7i. Again, let's remember what I squared is. It's negative 1. So minus 6 times negative 1 over 1 minus 4 times negative 1. Let's continue to simplify this. This negative 6 times negative 1 is positive 6, and 6 plus 5 is 11, plus 7i in my numerator. In my denominator, this negative 4 times negative 1 is positive 4 plus 1, which is 5. And if I wanted to write this in complex form, I'd like you to be in the habit of writing it as 11/5 plus 7/5 I. Break the fraction up. The last thing I want to talk about regarding complex numbers is how we can graph complex numbers in what we call the complex plane. And if I have a complex number, a plus bi, we would graph it as the point a comma b. So I'd hope that you'd realize that makes the x-axis our real axis and the b-axis the imaginary axis. We've talked about absolute value a little bit, and you know that the absolute value of a number is its distance from 0 on the number line. Similarly, we think of the absolute value of a complex number as its distance from 0, 0 in the complex plane. Let's take a look at what that would look like. So the first thing they're asking us in this example is simply to graph the number in the complex plane. So my number is 5 plus 2i. I would graph it as 5, 2, which is here. And if I wanted to find the distance from this point to 0, to 0, 0, I'd hope that you'd notice this right triangle that kind of presents itself. So, oh look, geometry, Pythagorean's theorem. Who'd have thunk it? So, if this is my absolute value, I'm going to call that d for distance. So, 2 squared plus 5 squared equals d squared. 4 plus 25, I'm getting ahead of myself. So since 4 plus 25 is 29, and I know I'm going to take the square root of both sides, d equals the square root of 29. And I hope you realize why I'm not putting a plus or minus sign here, even though I took the square root of both sides of an equation in order to solve for a variable. We're finding the distance of a point from 0, 0 on the coordinate plane. I can't have a negative distance. Same idea in this example. This point will be negative 3, 4. So negative 3, 4. This segment represents the absolute value of that complex number. It is found by, again, considering this right triangle. So 3 squared plus 4 squared equals d squared. So 9 plus 16 is 25. And when I take the square root of 25, I get just 5.